Hello everybody. So today we are going to discuss Jahn-Teller Distortion, which is one of the most important topic in coordination chemistry. So first of all, what is meant by distortion? Distortion, we say that it is a deviation from the regular geometry. Distortion is the deviation from the regular geometry of the complex, and this distortion is mainly proposed to explain the square planar geometry of copper complexes. So what are the types of distortions possible in octahedral geometry? So octahedral geometry, it is the perfect symmetrical geometry. So along the C4 axis, we can have two types of distortions. So in the octahedral geometry, where do we have the C4 axis? So this is the octahedral geometry. కొంచెం తీసేయండి అమ్మా ఇది. So when we see the octahedral geometry, where do we have the C4 axis? So this is Z axis, this is X axis, and this is Y axis, and the corners of octahedron. On the corners of octahedron, we have the 6 ligands. Now along any one of the XYZ axis, we can have the C4 axis, and the distortion along any one of the C4 axis, we get this is C4 axis. Along any one of the C4 axis, if there is distortion, we call it as tetragonal distortion. So octahedral geometry, it is a perfect geometry. Now along the C4 axis, we can have two types of distortion. So the first one is, we call it as tetragonal elongation, or we call it as Z out case, or we also call it as elongated octahedron. And the second type of distortion is tetragonal compression, or we call it as Z in case, or we call it as compressed octahedron. So why we call it as tetragonal elongation or compression? Because the distortion is along C4 axis. So we have two types of distortions along C4 axis. And why this distortion occurs, and what is the consequence of distortion? Distortion occurs mainly due to the asymmetric configuration with the metal electrons. When there is asymmetric configuration with metal electrons, the distortion occurs. And what is the consequence of distortion? As a result of distortion, the complex will reduce its symmetry. Energy is released, and this energy is going to remove the degeneracy of the d orbitals of metal. So if you take octahedral geometry, it is a perfect geometry, perfect cubic geometry, and when you take the elongation, that is distortion along C4 axis, whether it's tetragonal elongation or compression, the symmetry of the complex, it is reduced from octahedron to D4H. So the consequence of distortion is, first it will lose its symmetry, and due to the loss of symmetry, energy is released, and the degeneracy of d orbitals of metal is lost. So we say that distortion is due to the asymmetric configuration of metal electrons. Then what are symmetric and asymmetric configurations? That is half filled or completely filled orbitals. Half filled or completely filled orbitals, we call them as symmetric configurations. These are symmetric. So then what are asymmetric configurations? That is less than half filled, less than half filled or less than full filled. Less than fulfilled configurations, they become asymmetric. Or fulfilled orbitals or configuration, they become asymmetric. And the distortion is due to the asymmetric configuration, and as the consequence of distortion, symmetry is reduced, energy is released, which further splits the degeneracy of metal orbitals. So if you take the T2G set, T2G set, in this what are the symmetric and asymmetric configurations? Symmetric configurations are the half filled and completely filled orbitals. So T2G0, T2G3, T2G6, these are the symmetric configurations. And the asymmetric configurations, so what are asymmetric configurations? Less than half filled, T2G1, less than full filled, T2G1, T2G2, these are less than half filled, T2G4, T2G5, these are less than full filled. And if you take EG orbitals, so what is the symmetric configuration in EG? That is vacant orbital, EG0, EG4, these are symmetric. And the asymmetric configurations, asymmetric, that is less than half filled, EG1, less than full filled, EG3, are asymmetric. Now we are left with EG2 configuration. So this EG2, it becomes symmetric. Symmetric in weak field complexes. Symmetric in weak field, so where dx square minus y square orbital, dz square orbital, both of them carry one electron each, and it becomes asymmetric in strong field complexes. So in these complexes, the two electrons, they are present only in the dz square orbital. And the distortion is due to the asymmetric configurations of the metals. So when you take the example, Cu plus 2, Cu plus 2, it is a D9 system. We write the configuration as T2G6 EG3. So T2G6 is completely filled, so it is symmetric. It won't contribute for distortion. EG3, it is less than full filled, so it is asymmetric, and this is responsible for distortion. And this EG3 configuration we can represent in two ways. The first way of representation is we can take two electrons in dz square, one electron in dx square minus y square. Second case, that is two electrons in dx square minus y square and one electron in dz square orbital. Distortion is due to the repulsions caused by metal electrons on the ligand field. Metal electrons repel the ligand field, due to which the distortion occurs. So in the first case, let us see what is the type of distortion we are going to get. The ligands approaching the metal through the most populated axis. So here we have the z-axis where we have two electrons along the z-axis. x square minus y square. Along xy axis you have one electron. The ligands approaching the metal through the most populated axis are more repelled by the metal. And to minimize this repulsions, the ligands move away from the metal. So in the first case, there are more number of electrons along the z-axis. So along the z-axis, ligands experience more repulsions, and to minimize that repulsions, ligands along the z-axis move away from the metal. So this is going to produce the tetragonal elongation. So why we are calling it as elongation? Because two ligands along the z-axis are longer than the remaining four ligands. And we also call it as Z-out case. Z-out case. Two ligands along the z-axis are far away from the metal. We call it as Z-out case, or it is elongated octahedron. Elongated octahedron. Now when we take the second case, the most populated axis is x-axis and y-axis, where we have two electrons in dx square minus y square. So the ligands approaching the metal through the x and y-axis are more repelled by the metal. The ligands along the x and y axis, they are more repelled by the metal. The four ligands along the x axis move away from the metal, and this distortion we call it as tetragonal compression. And since the ligands along the z-axis are close to the metal, along the z-axis ligands are close to the metal, we call it as Z in case, or we can call it as compressed octahedron. Compressed octahedron. So till here it is the effect of metal. So metal is going to produce the repulsions on the ligand field, due to which the distortion occurs. And at the same time, ligands also, they have to repel the metal electrons. Both are simultaneous. Metal electrons repelling the ligands, or ligands repelling the metal electrons, both are simultaneous. When metal electrons repel the ligands, distortion occurs. When ligands repel the metal electrons, degeneracy of orbitals is lost. Now, how to identify the energies of orbitals? So in this, if you take the first case, tetragonal elongation, along the z-axis the ligands are away from the metal. Therefore, the orbital on the z-axis, so the orbital on the z-axis is nothing but dz square. And the orbitals close to the z-axis, orbitals close to the z-axis are dxz, dyz. Since the ligands along the z-axis are far away from the metal orbitals along the z-axis are close to the z-axis, experience less repulsions from the ligands. They experience less repulsions, so the energies of orbitals present along the z-axis or close to the z-axis will lose the energy. So what happens if you take the EG set? In EG set, dz square orbital is going to lose the energy since it is along the z-axis, and then dx square minus y square orbital is going to gain the energy. And the energy loss and gain here is represented as minus half delta 1 here, and the energy absorbed by dx square minus y square, it is half delta 1. And when you take T2G set, in T2G set the orbitals close to the z-axis are dxz, dyz. So they are going to lose the energy, and the orbital dxy, it is going to gain the energy. And what is the energy loss or gain here? Energy loss or gain. So that is dxz or dyz, they are going to lose the energy of minus 1 by 3 delta 1, whereas dxy, it is gaining the energy of 2 by 3 delta 2. సో ఇది ఒక్కటి తీసేయండి అమ్మ, కొంచెం T2G మళ్ళీ స్టార్టింగ్ నుంచి చెప్తాను. ఇక్కడ నుంచి ఇది ఒకటి T2G నుంచి. If you take T2G, the dxz and dyz, they are close to the z-axis. So these two orbitals are losing the energy, and the energy loss is minus 1 by 3 delta 2. dxy, it is gaining the energy, and its energy gain is plus 2 by 3 delta 2. So first metal is repelling the ligands, distortion occurs, then ligand field is going to repel the metal electrons, and that is going to split the degeneracy of metal orbitals. In the octahedral geometry, T2G and EG orbitals are degenerate. T2G orbitals are degenerate, EG orbitals are degenerate, but as the consequence of distortion, T2G and EG set of orbitals, they are further losing the degeneracy. So this energy difference, we take it as delta tetragonal. And now what is the increasing order of energies of orbitals in tetragonal elongation? That is dxz, dyz. They are degenerate, less than dxy, less than dz square, less than dx square minus y square. So this is the increasing order of energies of orbitals in tetragonal elongation. Now when we come to the second case, that is tetragonal compression. So in this, the ligands along the z-axis are close to the metal. Along the z-axis, the ligands are close to the metal. Therefore, the orbitals on the z-axis, that is dz square, orbital close to the z-axis, dxz or dyz, they experience more repulsions from the ligands. Ligands along z-axis are close to the metal, so the orbital on the z-axis, orbital close to the z-axis, they experience more repulsions from the metal, they are going to raise their energies. Or I can say that ligands along the x and y axis are far away from the metal, therefore the orbital on the x and y axis, that is dx square minus y square, and the orbital close to the xy axis, dxy, will lose the energy. We can represent in any way, in terms of repulsions or in terms of attractions. So ligands along the x and y axis are far away. So ligand on the xy axis, dx square, orbital on the xy axis, dx square minus y square, orbital close to the xy axis, that is dxy, lose the energy. So if you see the energy splitting, EG, in EG set, dx square minus y square is losing the energy, and dz square orbital gains the energy. And energy loss and gain, dx square minus y square is losing the energy in terms of minus half delta 1, and the energy gain by dz square orbital is minus half plus half delta 1. The energy lost by dx square minus y square is minus half delta 1. Energy gained by dz square is plus half delta 1. And if you take the T2G set, the ligand close to the orbital close to the xy axis, that is dxy, loses the energy, and the orbitals dxz, dyz, they are gaining the energy, and the energy loss and gain, dxy orbital is losing the energy by 2 by 3 delta 2, whereas dxz, dyz, they are gaining the energy by 1 by 3 delta 2. So this is delta octahedral, energy difference in octahedral field, and this is delta tetragonal. So now the increasing order of energies of orbitals in tetragonal compression, that is dxy less than dxz is equal to dyz less than dx square minus y square less than dz square. So this is the increasing order of energies of metal orbitals in tetragonal compression. How to identify whether the distortion occurs or not, and what is the nature of distortion? So one of the important application of Jahn-Teller distortion is, by seeing the complex we can just say whether the distortion exists or not, but we cannot say what is the type of distortion by observing the complex. Whether it is elongation or compression, we cannot say by observing the complex, but we can say whether the distortion exists or not. So how to identify the nature of distortion? That is, if T2G is symmetric and EG is symmetric, there is no distortion. No distortion means the complex is the perfect octahedron. Where all the metal ligand bond lengths are similar. And if T2G is asymmetric, and EG is symmetric, we say it as slight distortion. And if T2G is symmetric and EG is asymmetric, we have strong distortion. So what is the difference between the slight distortion and strong distortion? It is just the matter of difference in bond lengths. So if you take the metal and this is the ligand, if there is T2G orbital which is asymmetric, if T2G is asymmetric, T2G orbital is away from the ligand, so it cannot produce more repulsions on the ligand. Therefore, ligand is repelled by the metal to small extent. So this we call it as slight distortion. T2G orbital, it is away from the path of ligand, cannot repel the ligand more. So ligand will move only to certain distance. So we call it as slight distortion. But if you take EG orbital is exactly in the path of ligand, produce more repulsions on the ligand field. So ligand can move to greater distance. And asymmetric EG, it is going to cause the strong distortion. So the slight and strong distortions, they differ only in terms of bond lengths. And ఒక్కసారి ఇక్కడ ప్రొజెక్ట్ చేయరా, ఒక్క నిమిషం. In tetragonal elongation, two of the metal ligand bond lengths are longer than 4 metal ligand bond lengths. 2 metal ligand bond lengths are longer than 4 metal ligand bond lengths, means ligands along the z-axis, their bond lengths are more than the ligands along the x and y axis. And in tetragonal compression, 2 of the metal ligand bond lengths are shorter than 4 of the metal ligand bond lengths. Ligands along the z-axis are close to the metal, so their bond lengths are shorter than the metal ligand bond lengths along the x and y axis. Okay. So now what are the different type of questions we are going to get in this? It is one of the most important topic. At least you can expect one question from this Jahn-Teller distortion. So first of all, how to identify whether there is a distortion in the complex or not. So first, if I take the complex TiH2O taken 6 times 3 plus, whether the distortion exists or not. So in this, the oxidation state of metal is +3. In +3 state, D1 metal is D1 system, and this D1 system we write it as T2G1 EG0. T2G1 less than half filled. So here T2G is asymmetric, EG vacant orbital, so EG is symmetric. So which condition is applicable for us? T2G asymmetric, EG symmetric. So we get slight distortion. Slight distortion is observed. And when you take the other example, that is CrH2O taken 6 times 2 plus. CrH2O taken 6 times 2 plus, so here it is +2, it is D4, and water is the weak field system for chromium. So the configuration will be T2G3 EG1. So T2G is half filled, so it is symmetric. EG is less than full filled, so it is asymmetric. So which condition is applicable? T2G symmetric and EG asymmetric. So it is strong distortion. We observe strong distortion. And if you take the other example, that is CuCl6 4 minus, it is +2 D9 system. So we write the configuration T2G6 EG3, T2G6 completely filled, it is symmetric, EG less than full filled, it is asymmetric. So we observe strong distortion. So by observing the complex, by seeing the complex, we can just predict whether the distortion exists or not. But we cannot say which type of distortion exists, whether it is elongation or compression. So in order to understand that elongation, whether it is elongation or compression, we have to go for experimental observations. Okay. So what are the different type of questions we are going to expect in this? First one, CuX2. CuX2 in solid state. In solid state, it has 2 metal ligand bond lengths greater than the remaining 4 metal ligand bond lengths. So in this, what is the type of distortion? You have to identify what is the type of distortion. Second, arrange metal orbitals in increasing order of energies. Metal orbitals in the increasing order of energies. And then calculate Jahn-Teller stabilization energy. Jahn-Teller stabilization energy. So first one, Cu +2. it is D9 system. So we say that it is T2G6 EG3. Configuration is T2G6 EG3. It is given that 2 of the metal ligand bond lengths are longer than the remaining 4. Means the type of distortion, it is tetragonal elongation. 2 metal ligand bond lengths are longer than the remaining 4. Tetragonal elongation or Z out case. Then you have to arrange the metal orbitals in the increasing order of energy. So what is that? dxz is equal to dyz less than dxy less than dz square less than dx square minus y square. Now you have to calculate Jahn-Teller stabilization energy. So copper is D9 system. Arrange the 9 electrons in these orbitals. So that is 1, 2, 3, 4, 5, 6, then 7, 8 and 9. So now here in this, for dxz and dyz, what is the stabilization energy? Minus 1 by 3 into 4 electrons in these orbitals in terms of d2, delta 2, plus for dxy the energy is plus 2 by 3 into number of electrons 2 in terms of delta 2. So this is minus 4 by 3 delta 2 plus 4 by 3 delta 2. So the energy is 0 with respect to T2G. Now when you take Eg, so here for dz square the energy is minus half into 2 electrons in dz square plus dx square minus half y square plus half into 2 electrons delta 1. So what is the energy now? Here it is minus 1 delta 1 plus half delta 1. So the energy is minus half delta 1. So the Jahn-Teller stabilization energy is minus half delta 1. So you are generally asked to arrange the orbitals in the increasing order of energies and you are asked to calculate the stabilization energy. And the other question, that is solid MnF3. Solid MnF3 has 2 metal ligand bond lengths shorter than 4 metal ligand bond lengths. So now what is the type of distortion? You should identify the type of distortion, energies of orbitals, that is increasing order of energy of orbital. Arrange the orbitals in the increasing order of energies of orbitals and calculate Jahn-Teller stabilization energy. So Mn plus 3, it is D4 system, and fluoride ion, it is weak field. So it is given that 2 of the metal ligand bond lengths are shorter than 4 metal ligand bond lengths. Therefore, the type of distortion, it is tetragonal compression, or we can call it as Z in case. Increasing order of energies of orbitals, that is dxy less than dxz is equal to dyz less than dx square minus y square less than dz square. So this is the increasing order of energies. Now you are asked to calculate Jahn-Teller stabilization energy. Since Mn plus 3 is weak field, so we have to arrange the electrons in the weak field case. So in the weak field case, electron pairing starts after all the orbitals are half filled. So now what is the Jahn-Teller stabilization energy? ఒక్క నిమిషం ఆపండి అమ్మా. ఇది మొత్తం తీసేద్దాము. ఒక్కటి కొంచెం చిన్న మిస్టేక్ అయింది. ఈ క్వశ్చన్ నుంచి తీసేద్దాము. జస్ట్ కొంచెం చేంజ్ చేస్తాను అంతే. నేను చెప్తానులే, స్టార్ట్ చేస్తే అప్పుడు. సో ద సెకండ్ క్వశ్చన్ ఈజ్ solid FeF2 ferrous fluoride. It has 2 metal ligand bond lengths shorter than 4 metal ligand bond lengths. So you should identify the type of distortion. You should arrange the orbitals in the increasing order of energy and calculate Jahn-Teller stabilization energy. So in this metal is Fe plus 2, it is D6 weak field. So the type of distortion, since 2 metal ligand bond lengths are shorter than the remaining 4, we call it as tetragonal compression or Z in case. And the increasing order of energies of orbitals, dxy less than dxz dyz less than dx square minus y square dz square. And you should calculate the Jahn-Teller stabilization energy. Fe plus 2 is D6 weak field. So write the configuration for D6 system. Since it is weak field, all the orbitals must be half filled with electrons, 5 and then 6. So what is the Jahn-Teller stabilization energy? That is minus 2 by 3 into 2 electrons in terms of delta 2 plus 2 by 3 cancel out plus 1 by 3 plus 1 by 3 into 2 electrons in terms of delta 2 and minus half into 1 electron delta 1 plus half into 1 electron delta 1. So this is minus half plus half delta 1. So I can say that energy is 0 here, and here it is minus 2 by 3 into 2. It is minus 4 by 3 plus 1 by 3 into 2. It is plus 2 by 3 in terms of delta 2. So the resultant energy is minus 2 by 3 delta 2. So the Jahn-Teller stabilization energy is minus 2 by 3 delta 2. Okay. So let us see the questions that occurred in the previous years. So the first question, you are given the list of 4 complexes and you are asked to identify the complex which does not have ideal octahedral geometry. So what is meant by ideal octahedral geometry? Where all the metal ligand bond lengths are equal. Means you should identify the complex where the metal ligand bond lengths are not equal. Not equal means where, what is the complex that undergoes distortion. So finally you should identify the complex that undergoes distortion. So when you see the first option, it is Ni plus 2. Ni plus 2 is D8 system. So the configuration is T2G6EG2. So both are symmetric. Both are symmetric. There is no distortion. So it is all the metal ligand bond lengths are equal. So it is an ideal octahedral complex. Now second, Mn plus 2. Mn plus 2, it is D5 high spin. So configuration is T2G3EG2. Both are symmetric. Both are symmetric. There is no distortion. So it is an ideal octahedral complex. Now the third option, it is Cr plus 3. Cr plus 3 is a D3 system. So it is T2G3EG0. So T2G is symmetric. EG is also symmetric. So all the metal ligand, there is no distortion in the complex. All the bond lengths are similar. So this is also the ideal octahedral complex. Now titanium, it is titanium plus 3. Plus 3 D1 system. T2G1EG0. So T2G is asymmetric. So titanium complex, T2G is asymmetric, EG is symmetric. So titanium complex undergoes distortion. When distortion occurs, the geometry is not ideal octahedral because of the difference in bond lengths. Therefore, the answer for this is the titanium complex. And when you see the second question, they have given the set of complexes and they are saying that they have tetragonal elongation and compression in the complexes. So you have to identify the orbital which contains the unpaired electron. So when you take the first complex, that is K2BaCuNO2 taken 6 times. So it is undergoing tetragonal elongation. Tetragonal elongation. So Cu plus 2, it is a D9 system. And in elongation, what is the order of energies of orbitals? That is dxz is equal to dyz less than dxy less than dz square less than dx square minus y square in tetragonal elongation. So you have to write the configuration for 9 electrons. So 1, 2, from D7, D8 onwards, you won't find the effect of field strength. So you can write the configuration in the normal pattern. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So now you are asked to identify the unpaired electron. So in tetragonal elongation, the unpaired electron is present in dx square minus y square. In the first complex, unpaired electron is in dx square minus y square. Now when we take the second complex, that is B complex, CS2BaCuNO2 taken 6 times. So it is undergoing tetragonal compression. Tetragonal compression. So what is the complex? It is Cu plus 2 D9 system. The increasing order of energies of orbitals, that is dxy less than dxz is equal to dyz less than dx square minus y square less than dz square. So arrange 9 electrons in these orbitals. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Means in this complex, the unpaired electron is present in dz square. dz square. Now the third question, it is tetragonal elongated manganese acar complex. So the fourth d electron is present in the orbital. It is tetragonal elongation. It is Mn plus 3. It is D4 weak field. D4 weak field. So it is tetragonal elongation. and is saying that the fourth electron is present in which orbital. So the order of energies of orbitals, it is dxz is equal to dyz less than dxy less than dz square less than dx square minus y square. Fourth electron. So write the configuration for 4 electrons and say it is d4 weak field. So I should arrange 1 electron each in the orbital. So the fourth electron, it is present in dz square. And the next question, what is the correct statement regarding the complexes nickel and copper? So what he is saying, he is comparing in terms of bond lengths. If there is no distortion, all the metal ligand bond lengths will be similar. If there is distortion, either 2 metal ligand bond lengths will be longer than the remaining 4, or the 2 metal ligand bond lengths will be shorter than the remaining 4. Accordingly, we should find out the option. So first of all, if I take the nickel complex Ni plus 2, it is D8 system, T2G6 Eg2. So both are symmetric. So no distortion in nickel complex indicates that all the metal ligand bond lengths must be similar. All the nickel oxygen bond lengths must be similar. And when I take the copper complex Cu plus 2, it is D9 system, T2G6 Eg3. So T2G is symmetric, Eg is asymmetric, means we can have the distortion. But whether it is elongation or compression, we cannot identify by seeing the complex. So see the options. In the first option, he is saying that all the bond lengths are similar. No, only nickel complex will have all the bond lengths similar. In copper complex, you won't have similar bond lengths because of distortion. And if you take the second option, he is saying that nickel oxygen bond lengths are not similar. So you cannot take this option. Third option, all the nickel oxygen bond lengths are equal. Copper oxygen equatorial bond lengths are shorter than the axial copper oxygen bond lengths. So he is saying that all the nickel oxygen bond lengths are similar, means there is no distortion. In copper complex, yes, you can have the distortion. And there he is saying that axial copper oxygen bond lengths are longer than equatorial, which indicates that there is distortion. So your answer will be C. And if I go for D, he is saying that all the copper oxygen bond lengths are equal. No, there is distortion in the copper complex, so it cannot have all the metal ligand bond lengths equal. So your answer is C. Next, among the list of complexes given to you, you should identify which complex undergoes the Jahn-Teller distortion. So if you take the example, first question, that is, if you see the A complex, first complex, it is Cr plus 2, it is D4 low spin because cyanide is strong field ligand. So your configuration will be T2G4 Eg0. So T2G is asymmetric, Eg is symmetric. So you can have the distortion in the first complex. Second, B complex. So in this, the metal is cobalt plus 3, cyanide is strong field ligand. So we take it as D6 strong field. So the configuration is T2G6 Eg0. So both are symmetric. So there is no distortion in the complex. And if you go for C option, that is the metal is Fe plus 2, it is again D6 strong field. So it is T2G6 Eg0 both are symmetric, there is no distortion. So you won't find any distortion in the complex. And when we go for D option, metal is Mn plus 2, it is D5, cyanide is strong filled. So we write the configuration as T2G5 Eg0. So T2G5 is asymmetric and Eg0 is symmetric. So we find the distortion in D complex. So Jahn-Teller distortion is observed in A and D complexes, A and D. Now the next question is, Jahn-Teller distortion is expected for the configuration in Ml6 complexes is. You should find out in which configuration you are going to have the distortion. D1, we write it as T2G1. This erase cheyna? This erase cheyna? Adi record అయిపోతుంది కదా. Sixth మళ్ళీ చెప్తాను. So the last question is, Jahn-Teller distortion is expected for the configuration in Ml6 complex. So you are given with different options. Let us see them. First one, D1. So how do you write D1? It is T2G1 Eg0. So T2G is asymmetric. Asymmetric, Eg0 is symmetric. So you can observe the distortion. And if you take the second option, D3. D3, we write it as T2G3 Eg0. So both are symmetric. Both are symmetric. There is no distortion. No distortion in the configuration. Now D5 high spin. It is T2G3 Eg2. So both are symmetric. Both are half filled configurations. Both are symmetric. There is no distortion. And the fourth option, it is D6 low spin. So we write the configuration as T2G6 Eg0, T2G6 completely filled, symmetric, Eg0 vacant, symmetric. So no distortion in the complex. No distortion. So the answer for the question is A. So these are all the different type of questions you are being asked in the previous exams.